In this lecture video, we look at how to analyze data from a randomized complete block design. And so we'll start off with the data organization and the summarization of the data required for the analysis. And so this looks very similar to the layout, the organization, and the summarization that we had for the completely randomized design. But for the randomized complete block design, we have, in addition to the summary statistics for the treatments, we also have over here on the far right hand side, we have some summary statistics for the blocks as well. So I've got listed the block totals. All right, you'll also see that I have the block means. Now for the analysis of variance, we'll for the most part be using the block sums, but it is useful again to report the block means so that the researcher can get an idea of the variability from one block to another. Now again, just make sure that you understand that the first subscript here on the responses, on the Y's, corresponds to the block that the observation comes from, and the second subscript corresponds to the treatment that's been applied to the experimental unit. All right, and then also note that when we look here at the sums, for example, y sub 1 dot, that is the sum of the observations in the first block. The dot means that we're summing over all the treatments within that block. Similarly, y2 dot is the sum of the observations within block 2, and so forth. On the other hand, if we go down here and look at the sum for this column, receiving treatment 1, we see that the sum of the values across all of the R blocks that have received treatment 1 is represented by y dot 1. So again, the second subscript being 1 means that we're dealing with treatment 1, and we've summed up the observations for the experimental units that have received treatment 1 across all blocks. Okay, then in addition to the column sums, we have the column means. All right, so the means, the mean response for each treatment. And we also have the sum of squared values. All right, so the sum of the squared observations that have received treatment 1, the sum of the squared observations that have received treatment 2, and so forth. All right, once we have the summary statistics computed for that table, then we can begin to calculate the required values for the analysis of variance. On this particular slide and on the next slide, next two slides actually, I'm just denoting here several of the quantities that were calculated in this particular table. All right, so this is a nice way to organize it. It's a nice way to help us remember how to do the calculations. And again, the next three slides just show us the notation and show us the mathematical the mathematical formulas for each of these pieces of notation. All right, and so you can look at those, write those down for your notes. All right, so you see here that we have summary statistics for the treatments, summary statistics for the blocks, and then we have overall summary statistics as well. All right, and this is just another version of that same table where in the last row I have replaced the summation. Remember, this is the sum of squares for each of the treatments, right? And so I could also use this notation from the previous slide. Let me see here, go back here. The uncorrected sum of squares, which is just the sum of the values of the squared observations for each treatment. And you can see here how we calculate that. So it's just another way to represent notationally the values that go in that last row. Okay, so once we have those summary statistics, then we can very easily calculate the quantities needed for the analysis of variance. First, as was the case for the completely randomized design, we have to calculate the correction term, which we're denoting by cap C. And so that is just the square of the overall sum of the values in the data, right? So we add up all the responses in the data and then square that sum, and then we divide that by the total number of observations in the sample. And for a completely randomized design with T treatments and R blocks, that total number of observations would be T times R. Now, once we have the correction term, then it's very easy to calculate the total corrected sum of squares. We just subtract the correction term from the total uncorrected sum of squares, which is one of the summary values provided in that summary table. We then compute the block sum of squares, the sum of squares due to blocks, and so that is given by this expression. So 1 over t, 1 over the number of treatments, times the sum, I going from 1 up to r. Now notice that we're summing over the blocks. Remember I, the first subscript corresponds to the blocks, and there are r of those. So we're summing up. What are we summing up here? Well, we are taking the block sum and squaring that block sum for each block, and then we're adding those squared block sums up, multiplying by 1 over t, where t is the number of treatments, and then from that we're subtracting the correction term. So it may seem kind of counterintuitive that we divide by, we're adding up r things, but we're dividing by t, but that's the way the mathematics works out. All right, then the treatment sum of squares, the SST value, and this is similar to what we saw for the block sum of squares, but now what we're doing is summing up squared values, the treatment sums, and we're dividing by r, which is the number of blocks. And so we do this calculation, and then from that subtract the correction term. And then once we have those three terms, the total corrected sum of squares, the block sum of squares, and the treatment sum of squares, then we calculate the sum of squares error by subtraction. So we subtract the sum of the block sum of squares and the treatment sum of squares from the total corrected sum of squares. And when we distribute that minus sign across the sum, then it becomes that quantity right there. Okay, so here is the structure of the ANOVA table for a randomized complete block design. We see that the what we've done, this looks similar to the ANOVA table for the completely randomized design, but now we have an extra source of variation, all right? And we'll list that first. We have a source of variation due to blocks. And what we're doing is we're removing that amount of variation from the total variation. I'm sorry, from the error variation, all right? The error variation is that which is unaccounted for by the rest of the model. In the completely randomized design, the only accounted for variation was due to treatments. And so all other variation was unaccounted for, and it showed up in that row. But now what we're doing is we are trying to pull out variation due to blocks, and so we're pulling that variation out of the error variation. Okay, so we have R blocks, and so there are R minus 1 degrees of freedom associated with blocks. We have T treatments, and so the number of degrees of freedom associated with treatments is T minus 1. There we have a total of T times R observations, experimental units, and so the total number of degrees of freedom is T times R minus 1, so 1 less than the total number of observations. And then the total number of the number of degrees of freedom associated with the error term is equal to the product of R minus 1 and T minus 1. Well, you'll notice that that is the product of the numbers of degrees of freedom associated with blocks and with treatments. And what this essentially represents is the interaction between, we can think of it as the interaction between blocks and treatments. Now, let me just say, one of the assumptions is in a randomized complete block design, where we have where each treatment is represented exactly once in each block, there is necessarily an assumption that there is no interaction between blocks and treatments. In other words, that the differences between treatments are the same across the various blocks in the experiment. And so the implication of that assumption is that what we might call the interaction between blocks and treatments constitutes experimental error. And so that is why this works out this way. Okay, so then we have the sums of squares column, and again we represent the block sum of squares by SSR, the treatment sum of squares by SST, the error sum of squares by SSE, and then the total sum of squares by SS tot. Now, as is usual, we get the mean squares values, the values in the mean square column, by dividing the values in the sum of squares by the corresponding values in the degrees of freedom column. So the mean square for the blocks is SSR over R minus 1. The mean squares for treatments is equal to the sum of squares for treatments, SST, divided by its degrees of freedom, T minus 1. And then the mean squared error is equal to the sum of squared error divided by its degrees of freedom. Okay, and then finally, we can compute F statistics, and we could actually calculate an F statistic for blocks and an F statistic for treatments, although the F statistic for treatments is the one that we will always be interested in. We may or may not really be interested in the F statistic for blocks because we really can't get a valid p-value for that. It's just kind of a I'll try to explain that a little bit later, but this is really nothing more than an indication of whether blocks are significant, because we don't, and the reason is we don't have replication of blocks. Okay, so this is the structure of the ANOVA table. Right? Again, it's very similar to that for the completely randomized design. The difference being that we have a row for blocks now, and the purpose, what's happening here with that new row is that we are pulling out from the error term, from the error variation, that variability that is associated with blocks. And by doing that, we are going to make, as long as this reduction, as long as the reduction in the SSE is more than the reduction in the error degrees of freedom, okay, then this will increase the power of our hypothesis tests and the precision of our estimators. Now let's look at the expected mean squares and the hypotheses associated with the analysis of variance. Right? It's very important for us to understand this, and we looked at this in the context of a completely randomized design. And so to do this, we're going to look at the expected mean squares for blocks and for treatments and for error, so all three of these sources of variation. And so let's first look at the expected mean squares for error. All right, so the the mean squared error, MSE, is a random variable, and therefore it has a distribution. And that distribution, which we call its sampling distribution, has a mean. And the mean of that sampling distribution is called the expected value of MSE, or the expected mean square for error. And it turns out that regardless of whether the null hypothesis is true, and let's focus first on the fixed, so if we have a fixed effects model, so if the treatment effects are fixed. So with that in mind, regardless of whether the null hypothesis is true, the expected value of MSE is always going to be sigma squared. Okay, now let's look at the expected mean squares for treatments, again, for that situation where treatments are fixed effects. So, in general, the expected value of MST, the mean square for treatments, is given by this expression here, sigma squared plus something that is going to be positive because the number of replications is positive, and we're looking at the square of the treatment effects, so that would be positive as well. And so if the null hypothesis, now if the null hypothesis is true, so that all of the alphas are 0, then this whole term goes away. And so the expected mean square for treatments would be sigma squared, just like the expected value of MSE. And so if that's the case, then MST and MSE would be estimating the same quantity, and so their ratio would tend to be close to 1. On the other hand, if the null hypothesis is not true, so that the alphas are non-zero, then this quantity, expected value of MST will be estimating something larger than sigma squared, and so their ratio would tend to be larger than 1. All right, and so that's why we would look for large values of the F statistic. Okay, now let's look at the expected mean square for blocks. And so again, in this first column here that says fixed, this is what we're talking about, is that the treatment effects are fixed. Keep in mind that the blocks are always considered to be random variables, so that the blocks have mean of 0, and they have a variance which is denoted by sigma squared sub beta. And so what this is showing here is that the expected value of MSR, the expected mean square for blocks, is always going to be estimating this quantity here, sigma squared plus something positive. You know, as long as the variability associated with blocks is non-zero, if it's positive, then the expected value of MSR is estimating something larger than sigma squared. All right. Now, if blocking is effective, right, if the researcher understands the characteristics of the experimental material, again, perhaps a field or something like that, and has a strong reason to believe that there is variation from one block to another, then in that case sigma squared sub beta could a priori be believed to be positive, and so the expected value of MSR is estimating something larger than sigma squared. Now, this can be used to come up with kind of an intuitive, well, I call it a test, but again, since we don't have replication for blocks, it's not technically a formal test, but we can use this to get an idea, or it motivates why we would look at the F statistic in the ANOVA table, this first F statistic for blocks. That's what motivates that. But again, that's really nothing more than a rule of, or kind of an intuitive or informal way of looking at whether blocking has been effective. Okay, now let's look at the last column here, which are the expected mean squares for a random effects model, so a random treatment effects model. So in that case, and we'll start here at the bottom again, regardless of whether the null hypothesis is true regarding the treatments, the expected value of MSE will always be equal to sigma squared. So MSE is always going to be our estimate of sigma squared. Now, for the expected value of MST so the expected mean square for treatments, okay, under a random treatment effects model, that expectation is equal to sigma squared plus R, the number of blocks, times sigma squared sub tau, which is the variability associated with the random treatments. Okay? These two quantities in the last two rows, sigma squared plus R times sigma squared sub tau, and sigma squared will be equal if and only if sigma squared sub tau is equal to 0. So in other words, if there's no variability among the treatments in the population. And so that is what motivates our looking at this test statistic, that same test statistic in the context of a random treatment effects model. And then finally, notice that the expected value for the mean squares for blocks is the same, regardless of whether we're talking about a fixed treatment effects model or a random treatment effects model. Okay, so that leads us then to the hypotheses that are being tested by the ANOVA. So for the fixed effects model, the fixed treatment effects model, the F statistic follows the F distribution if and only if this quantity here is 0, which is true if and only if all of the alpha sub j's are 0. All right, so if and only if all of the treatment effects are 0. And so what that means is, the implication is that the hypothesis being tested by the F statistic for the fixed effects model is given by the following set of hypotheses. The null hypothesis being that all of the treatment effects are zero, against the alternative that at least one of the treatment effects is non-zero. And really, if because they have to add up to zero, if one was non-zero, then there would be another one that's non-zero. So keep that in mind. But anyway, you understand what the point I'm trying to make here. All right. And we could also express these hypotheses in terms of the notation from a means model. All right. So the null hypothesis would be that the means of all the treatments are the same. There's no differences among the treatment means, against the alternative that differences do in fact exist among the treatment means. All right, and then for the random treatment effects model, the F statistic follows the F distribution if and only if sigma squared sub tau is equal to 0, as we had indicated when we looked at that expected mean squares. And so that implies that the hypotheses being tested by the F statistic for the random treatment effects model is given by the following set of hypotheses. Sigma squared sub tau being equal to 0, that's the null hypothesis. So that would indicate then that there's no variability among the treatments in the population of treatments, against the alternative that there is in fact variability among the treatments within the entire population of treatments. And then again, these hypotheses can be stated in words in the following way. No differences exist among the treatment means across the entire population of treatments, being the null hypothesis, against the alternative hypothesis, which says that differences do in fact exist among at least some of the treatment means in the population of treatments. And then finally, regardless of whether we're working with a random treatment effects model or a fixed treatment effects model, the rejection criteria is the same. Right? The rejection rule is to reject the null hypothesis, H sub 0, if our test statistic for the treatment, kappa F sub t, is greater than the upper alpha percentage point of the F distribution with t minus 1 numerator degrees of freedom and denominator degrees of freedom equal to the error degrees of freedom in the ANOVA, which is r minus 1 times t minus 1. So that is the procedure for performing the analysis of variance in the context of a randomized complete block design and the hypotheses that are being tested by the ANOVA. Again, the hypotheses, the specific hypotheses, depend on whether we're talking about a fixed treatment effects model or a random treatment effects model. But they are essentially, in terms of the interpretation or the intuitive meaning of the hypotheses, they're roughly the same. Right? We're assuming that there's no variation, there's no variability due to treatments. There's no effect, there's no impact of the treatments on the response. That's the null hypothesis. Against the alternative hypothesis that the treatments do impact the response, that there is variability due to the treatments. And so that wraps up this particular lecture video. We'll pick it up in the next video and we'll look at an example of doing the analysis.